Assalamu alaikum. Welcome to the new lecture. In this lecture, we'll be discussing about a new topic that is about the insulated cables. The insulated cable can be defined as a single conductor insulated throughout its length, or two or more conductors each provide with its own insulation and laid up together under one outer protective covering. This is how an insulated cable can be defined. They are usually used for transmission and distribution of the power, where it is very difficult or almost impossible to make the use of overhead construction like congested urban areas or via right of way would be excessive or excessively expensive. So in that case, we are helpless to use the insulated cables. The problem with the insulated cables is that their initial cost is extremely high, which is one of the main reasons to discourage its use. Cable installation is usually used for submarines, crossways, railway yards inside of a power station, and densely populated areas. These are actually those areas where it is very difficult to install an overhead transmission line. That's why we go for the cable or insulated cables. All electric cables consist of three essential parts: the conductor for transmission of the electrical power, the insulation and electrical insulating medium needed to insulate the conductor from the direct contact with earth or other subjects, and the external protection against mechanical damage, chemical or electrochemical attack, fire, or any dangerous effect external to the cable. So these are three main parts of a cable. Now let us first try to see what are the different, what is the, how do we compare it with the overhead line. So you can see the public safety in case of underground cable is safer as compared to the overhead line. Initial cost that I have told you that is very high for this underground cable. This is relatively less. Working voltage is up to 66 kV. This is up to 400 kV. It may go up to in certain levels beyond that, but usually we restrict its use up to 66 kV because there is one more disadvantage, that's known as charging current. The charging current for the overhead cable is also more as compared to the overhead line because of the closeness of the conductors and the use of dielectric. Uh, this is one more disadvantage of the overhead line. Sorry, cable, underground cable. Maintenance cost is very low. Here is very high. Frequency of the faults is less. Here is very high. Frequency of the accidents is low. Here it is very high. Voltage drop is low due to less spacing. Here it is very high. Fault location or repairs, it is very difficult here because it is closed. It has got different protective covering. So to locate the fault is difficult. Here it is very easy. Charging current is high, as I told you. Jointing is slightly difficult as compared to overhead line. Damage to lightning is negligible. Here it is very high. Surge effect is absorbed by the sheath because sheath is at our potential. It is more affected, and for that case we use a surge arrestor. Interference with the communication lines. There is no interference because of the sheath which is at our potential. They actually provide the path to the different frequencies, the high frequency signals to the earth, which is not the case in case of this overhead line. So these are different points of the comparison of underground cable and overhead line. Now classification of cable usually depends upon the location and mechanical consideration. So as per the voltage level, we can classify the different cables like this. We have low voltage cable are known as low potential cable or LT cable. It is used up to 1 kV. High voltage cable or high tension cable, it is, or HT cable, used up to 11 kV. Super tension cable, ST cables, it is used up to 33 kV. Extra high tension cable, EHT cables, it is used up to 66 kV. Extra high voltage cables, there may be some cable which may be used up to 132, 400 or 500 kV also, but it is very rarely used, and these are known as super tension, super voltage cables up to 132 kV. A multi-core cable may be 2 core, 3 core or 4 cores four core, because three core means three phase, four core means three phase and a neutral. For a three phase, three wire system, either three single core cables or three core cable can be used depending on the operating voltage and load demand. We can have a different single core three cables. We can make them the three used for the three phase system, or we may have the inbuilt three core cable we can be used for the three phase system. The general construction of the cable, it has usually six parts. One is the aluminum conductor or copper conductor, that's over here. This is the conductor. Insulation or dielectric, that is placed over here, which separates it from the sheath and other conductors. Other one is the sheath, that is this one. This is the sheath. Sorry, this one is the sheath. And electrically, we are always interested with these three parts, that's conductor, insulation, and sheath, because sheath is at ground potential, this is at the actual potential, and this is the dielectric. So these are for the mechanical support, all these three parts. That is bedding. This is the bedding made of steel, and this is armoring. This is the armoring, and then the serving, over which we have a bedding and serving may be made of the same material. So this is to protect the armoring from the external damage. Now, starting from the aluminum conductor, or it may be, in most of the cases, you will see aluminum conductor used, but sometimes copper conductors are also used. An underground cable consists of one central core or a number of cores, two, three, or four, of standard copper or aluminum conductor, which provide paths for the power transmission. Insulation or dielectric. Insulation or dielectric is in an underground cable withstands operating voltage, because this provides we can say insulation between the conductor and the sheath. And the sheath, please try to remember, is at our potential. The aluminum conductor is insulated from each other by the paper or varnished cambric or vulcanized bitumen or impregnated paper. For up to 11 kV high voltage system, paper insulation is used. When oil is used as an insulating material, then it is called oil-filled cables, which is used to avoid the formation of the voids, air voids. Oil-filled cables require small amount of insulation and are used for the high voltage up to 66 to 400 kV. Sometimes SF6 gas, actually SF6 gas is used as a dielectric medium in a gas-filled cable, because the SF6 has a good insulating properties, and because of its insulating property, it is sometimes used as dielectric medium. One advantage of the gas-filled cable is that it is better heat dissipation by natural convection in the gas. Oil-filled and gas-filled cables are used in the range of this voltage level. So oil-filled and gas-filled cables to construct is slightly difficult. That is why the general cables that we use are only up to 66 kV. When we go beyond the 66 kV, we have to use oil-filled and gas-filled cables. Now, sheath. A metallic sheath of lead or alloy of aluminium or alloy or of aluminium is provided around the insulation to protect it against the ingress of the moisture. This is one of the important works of the sheath. It provides that it protects the conductor or this insulation from the moisture or gases or other damaging liquids like acids or alkalis in the soil and atmosphere. The main advantage of the lead sheets are the comparative ease with which they are made in the lead presses, their flexibility and high corrosion resistance. While they have got the drawback of large specific gravity, low mechanical strength, fluidity, and small resistance to the vibrations. Now another is the bedding. A layer of bedding which consists of the paper tape compounded with the fibrous material, maybe of jute or cotton, is provided over the metallic sheath for the protection of metallic sheath against the corrosion and from the mechanical injury. Over the layer of bedding, we have armoring, consists of one or two layers of galvanized steel tape, which is provided to save the cable from the mechanical injury. And the last one is the serving provided over the armoring. It is a layer of fibrous material similar to that of bedding. It is provided in order to protect the armoring. Single core cables for AC system are not provided with armoring because eddy currents induced in the steel armor cause additional power loss. In such cables, mechanical protection is provided by plastic wrap. Now, insulating materials. Let us see what are the different insulating materials and what should be the properties of different insulating materials. Aluminum or copper conductors are insulated from each other and from the sheath by the means of insulating material. The satisfactory operation of the cable depends to a great extent upon the characteristic of the insulation used. Therefore, the proper choice of the insulating material for the cables is of considerable importance. In general, the insulating material used in cables should have the following properties. It should have high insulation resistance to avoid the leakage current. It should have high dielectric strength to avoid electrical breakdown of the cable. That means usually what air does in between the conductors in case of overhead lines, same should be done by the insulating when it is used in the cable, because it provides a separation between the conductor and the sheath, which is at the potential. It should have high mechanical strength to withstand the mechanical handling of cables. It should be non-hygroscopic, that it should not absorb moisture from air or soil. It should be non-inflammable. It should have a low cost so as to make the underground cable system a viable proposition, unaffected by acids and alkalis to avoid any chemical action. These are the different properties of the can say an insulating material. Now, the commonly used materials are rubber, vulcanized India rubber. We have impregnated paper, varnished cambric, polyvinyl chloride, polyethylene, or cross-linked polyethylene, which is also known as XLPE. So let us have a look at the different insulating materials and their comparative analysis. This is rubber, impregnated paper, polyvinyl chloride, polyethylene, and this is also known as PVC. This is XLPE. The dielectric strength is given like this. This is 30 kilowatt per mm. It's not per centimeter. In case of air, it is 30 kilowatt per centimeter. So rubber has a dielectric strength of 10 times as that of the air. Similarly, for the impregnated paper, polyvinyl chloride slightly less. So cross-linked polyethylene slightly less. It may be having a similar sort of the value, but I haven't the exact value of this. So I have kept it as it is. So ER, that is the relative permittivity of the rubber, is 2 to 3. Polyvinyl chloride is 5. Temperature is another important parameter. For this, it is 60 to 670 degrees centigrade. It works well. This is up to 95 degrees centigrade. This is up to 75 degrees centigrade. This is up to 100 degrees centigrade, and this is up to 90 degrees centigrade. So the disadvantage for this rubber is that it is swells when exposed to light. So and also due to aging, and which restricts its use. And usually it is not used as an insulating material nowadays. Nowadays, cross-linked polyethylene or polyvinyl chloride mostly used. So impregnated paper is also used. It is usually used in low voltage and polyvinyl chloride industries for the light and power installation, and cross-linked polyethylene used for 33 kV. Low, because of it is low water absorption. It is hydrophobic in nature. So this is the advantage of this cross-linked polyethylene. Now coming to the electrostatic stress in a single core cable, let us try to have a look at this. We'll assume that we have a conductor over here whose radius is R, and when we use it in a cable, we assume that we have the inner radius of this sheath as denoted by the capital R. So in between this conductor and sheath, we have a dielectric whose permittivity is given by epsilon, and let this conductor has a charge per unit length of lambda, and let this conductor be at a potential of V with respect to sheath, and let G be the gradient at a distance of x from the center of the conductor within the dielectric material, that is from R to any, let's say this point, which is a distance of x from this R, and this x is less than R, and this G can be given by lambda divided by 2 pi epsilon x, which is also equal to actually E is the electric field. So which we have already calculated in corona, where we have discussed about the corona loss uh, and the critical disruptive voltage. We use this equation and we have derived this equation as well there. So this is the same equation. So here is the electric field intensity and lambda is the charge per unit length. So maybe in that case, the only difference is that we have used epsilon naught in case of epsilon, because here epsilon will be equal to epsilon r into epsilon naught, and in this case epsilon r has some value which is greater than 1. And now we know that V is equal to minus integral from capital R to small r, that's from here to here. When we have to calculate the voltage, we actually take the test charge from infinity to that point where we have to calculate the potential. So same thing, we have assumed this to be the infinite, actually the interest of point of interest, that is the R and this R. So consuming the minus inside this integral, these two will flip, or they will change their position. So that means the integral will be from small r to capital R, lambda divided by 2 pi epsilon x, because E is equal to lambda divided by 2 pi epsilon x dx. When we integrate it, dx by integral of dx by dx will be ln x from r to r, that is ln of r by r. Since g is equal to lambda divided by 2 pi epsilon x, that means lambda divided by 2 pi epsilon, which is in this, will be equal to g into x. Or we can say this g is equal to lambda divided by 2 pi epsilon x. So g is over here. So lambda divided by 2 pi epsilon is equal to v divided by ln of r by r. So it comes out with g is equal to v divided by x. That is this v divided by x into ln of r by r. So this is the value of the potential gradient at the point x from the center of the conductor. And this x should be between this small r and capital R. From the above equation for the gradient, it's clear that the gradient is maximum when x is equal to r, because our interest of region is from small r to capital R. When r is equal to and x is equal to small r, gradient will be maximum because r has a least value. When r has a maximum value, that is when x has a maximum value r, capital R, then g will have a minimum value. So the gradient will have a maximum at x is equal to r, that is the maximum at the surface of the conductor, and its value is given by this. Gmax is equal to v divided by r, small r ln of r by r, and g minimum will be equal to v divided by r ln of r by r. So in order to keep the fixed overall size of the cable r, that is fixed r, for a particular operating voltage, that is we have fixed v, there is a particular value of radius, which is the radius of the conductor, which gives a minimum gradient at the surface of the conductor. Because this is the maximum, we have to minimize this. We just want to have a minimum value of Gmax, because which is at lies at the can say surface of the conductor. We want to minimize this, not this Gmax. The objective here is to find the minimum value of Gmax, that is to maximize Fr. That is this R. When we maximize this, we'll get minimum value of this. So since V is fixed, so we can maximize this. That means we are overall minimizing this value. So when we differentiate it, dfr by r dr, that is this value. So it comes out to be minus r, and the differentiation of ln by capital R by r, that will be its reciprocal, that is minus r into r by r, into the internal differentiation of the r by r, that is r by r square, plus the differentiation of the r, that is 1. Ln of r by r remains as it is. This r square will cancel out, this r and r will cancel out, that means ln of r by r is equal to 1, r by r is equal to E. So from this it is clear that to have a minimum value of the gradient at the surface of the conductor, the inner radius of the sheet and the conductor are related with this equation. So a plot of the gradient at the surface of the conductor, and the ratio of this is given. When you plot this Gmax and R by R, I will get this type of a plot. That means it have a minimum value when R by R is equal to small r by r is equal to 1 by E, or R by R is equal to capital R by R is equal to E. In that case, we get this type of a curve. So this is how this can be done. One more thing that we need to understand, that we have to understand this stable and unstable operation. Let the ratio R by R corresponding to Q, point Q at this point on the curve in the above figure. Okay. Now, due to some manufacturing defects, say a thin film of air surrounds the conductor, which is trapped inside this dielectric sheet. This is a thin film of air. Let the thickness of this film be A units. Let's say this thickness is A. Since the working dielectric strength of the insulating material is taken about 40 to 50 kilovolt per centimeter, or even it may be greater than this. We have seen from the table that rubber has 30, which is 10 times that of the air. That means 300 kilovolt per centimeter. So I have here chosen 40 to 50 just to make you understand that its dielectric strength is greater than the dielectric strength of the air. To which now the air surrounding the conductor is stressed. Since the dielectric strength of air is more as compared to the air, this becomes conducting because its dielectric strength is only 30 kilovolt. It can bear up to only 30 kilovolt per centimeter. So here the voltage is gradient is more, it will be conducting now. So which gets and therefore the effective radius of the conductor it becomes conducting and the effective radius becomes R plus A divided by R. That means it changes from Q to Q dash. Corresponding to this ratio, the operating point is Q dash, that is the stress to which the dielectric material is subject is increased. Because from here to here, you can see this is the stress, it has increased. And this may finally lead to the rupture of the material because it has increased from the earlier value to the new value, which is still greater than the value of the earlier value, and it may result in the rupture of the insulating material. That is why from this point to this point is an unstable region. This situation will arise for all operating points to be of the right of the minimum point of the curve on the curve in this figure. So the points which are to the right side of the minimum point in the curve, we can call them that this area is an unstable region. Now let's take the cable, the R by R ratio corresponding to point P on this curve that is left to the minimum point. Say again, due to similar reasons, if the radius becomes R plus R and the ratio R plus area by R, then the operating point shifts to a point P dash where the dielectric material is subject to a relatively smaller dielectric stress than the point P. When it changes from P to P dash, even if uh, the radius is increased to R plus A, this point has shifted to this point. That means the dielectric strength has decreased. So there will not be any rupturing of the dielectric material. So this area from R by R is equal to, we can say, 0 to this. It is stable region. Therefore, it can be seen that all ratios are less than the minimum. That's 1 by E. The cable operates satisfactorily. This means for the satisfactory operation of the cable, R by R should be less than 1 by E, or R by R should be greater than E, or R should be greater than E small r. So this is how we have to be very careful. Now let us try to do some numericals on this overall economical diameter of the cable. In this numerical, we're asked to find out the economic overall diameter of a single core cable metal sheet for a working voltage of 85 kilovolt if the dielectric strength of the insulating material is 65 kilovolt per centimeter. You can see it from here. We'll be using this equation, and we have to find out the value of this R for a uh, economical overall diameter. That means when this R by R is equal to E. So when this R by R is equal to E, because you can see it from here, this R by R when it's equal to E, that's what this equation has written. For the economical size, the ratio of the outer diameter to the conductor diameter should be E. That is V R G max ln of R1 by R, it's actually capital R by R, is equal to R G max ln of E, which is equal to 1, that's called R G max. So R is equal to or R is equal to V by G max. V is equal to 85 kilovolt, G max is 65, which comes out to be 1.3 centimeters. So diameter of the conductor will be 2.6, and diameter of the sheath will be equal to E multiplied by this 2.6, that is 7.07 centimeters. This is how we can actually design this on the basis of these parameters. Now let us try to find out the insulation resistance of a cable. In this case, we know that usually the current flows through the core of the cable, actually along the core of the cable. That means if this is a conductor, the current flow may be into the plane of this page or out of the plane of this page. But the leakage current, that is current which is not useful, flows radially. It flows radially outwards from the conductor to sheath. Its direction is like this, which is shown in the dotted lines over here. Usually the resistance of the material is given by, it remains as it is, it will not change. Rho is the specific gravity or resistivity of the material, L is the total length of the conductor along which the current flows. Here the length will be from this point to this point. This is the length that this L corresponds to. And A is the area of cross section which uh, this uh, current faces. Where it flows, it faces the area. That area is considered over here in every case. Because if conductor is this, its area is pi r square. This is small r, pi into small r square. So the usual area for the uh, load current will be pi into small r square. But here the area will be, that is curved surface area of this conductor, because the current faces that much of that area, not this conductor cross section area. Or we can say of area A is the cross section normal to the flow of the current. So let us use these concepts of the resistance. We can calculate the insulation resistance of the cable. Let's say this is the conductor whose radius is R1, and the distance from center of this conductor and to sheath is R2, and we're assuming an elemental distance or elemental part of this dielectric, which is whose thickness is dx and which is at a distance of x from the center of this we can say conductor. So the radius insulation resistance of the layer of this layer, let's call it a dr is equal to rho. It will be independent of the length and the area. It will be as it is. It will be equal to dx, that is the length from here to here, because current will flow from this point to this point in this elemental area or elemental part length, dx divided by area in which is normal to this current, or we can say which wire current faces this area, and this area is actually 2 pi, the curved surface area of the cylinder, that is 2 pi the radius of the cylinder multiplied by length of the cylinder. Radius of the cylinder is x, and the length of the cylinder or the conductor is L, that is equal to 2 pi x into L. The total resistance will be resistance from R1 to R, from this point to this point, and dx divided by 2 pi x into L. So when you integrate it, it will be equal to rho 2 pi L ln of R2 by R1. R2 is actually radius of the sheath from the center of the conductor, which we have denoted usually by the capital R. So it comes to rho divided by 2 pi ln of R by R ohms. So here we have one important point to be noted, that the resistance of the core of the cable is directly proportional to the length of the cable. As length increases, resistance increases. But the leakage resistance is inversely proportional to the length of the cable. You can see over here. It is because of uh, the, the flow of the current is not radially along the conductor. It is uh, normal to the surface of the conductor from conductor to sheath. This shows that the insulation resistance of a cable is inversely proportional to the length. In other words, if the cable length increases, the insulation resistance decreases, and vice versa. This is a very important point regarding the insulation resistance. So I may summarize over here. There are three resistances, or in general impedances we can say. The characteristic impedance is independent of the line length. The normal resistance depends is directly proportional to the line length, and the insulation resistance is inversely proportional to the line length. So these 3 points are very important. You should remember these. Now let us try to do one numerical on the insulation resistance. The insulation resistance is given for a single core cable to be 495 mega ohm per kilometer, and this insulation resistance will be always of the order of mega ohms. So if the core diameter is 2.5 centimeter and the resistivity is 4.5 into 10 to the power 4 ohm centimeter, find the insulation thickness. So we need to find out the insulation thickness. So length of the cable L is given to be, because it is per kilometer, 100 meter, 100,000 meter. Cable insulation resistance given is 495 into 10 to the power 6 ohms. Conductor radius, that's R1, is 1.25 centimeter, that's 2.5 divided by 2. And resistivity of the insulation is 4.5 into 10 to the power 14 ohm centimeter. It's ohm centimeter. We have to convert into ohm meter. It will be equal to 4.5 into 10 to the power 12 ohm meter. So using the same formula that we have used, rho is equal, R is equal to rho 2 pi L ln of R2 by R1. So ln of R2 by R1 is 2 pi RL by rho, because all these parameters are known. It's 2 pi L is 1000. R is just 495 into 10 to the power 6. This is 4.5 into 10 to the power 12. So this comes out to be 0.69. So when you find out R2 comes out to be 2.5 centimeters. Actually radius of the sheet. The insulation thickness will be equal to difference of R2 and R1, that is 2.5 minus 1.25, that's equal to 1.25 centimeters. Okay, thank you. I'll stop over here.